Welcome to another live stream on the assumptions of physics, where we are trying to see where we are in the research and see if we can discuss open problems and do advance anything. Today we are going to look essentially at some of the problems that I have to extend some of the results that we have in classical mechanics to field theories. And there are a number of open problems associated with them, so I'll basically go through a bunch of things, and then if people want me to stop and go more in detail in any of them, please let me know. Okay, so I will try using the whiteboard for Zoom to write on it from my tablet, so hopefully this works. Let's see. Okay, so I see it on my screen, and I think it's also on the live stream. Of course, it would be nice if somebody could confirm that, but let's assume that everything is working fine. Okay, so the way that we have set up things in reverse physics for classical mechanics is that the notion of counter states is very important, and in fact the notion of having a counter state that it's invariant under coordinate transformation reference change. And so we basically need to have something like that for the field themselves. So instead of just changing the coordinates, we also need to be able to change essentially the units for the field. How do we represent the field? So here's how it should work. In let's say if we have a discrete set of states, let's see, can I move this away and I still draw? No, I need this to be able to draw. Okay, I'm learning how to use this thing. So if you have just a simple discrete, okay, I can't put my, okay, so this is going to be awkward to draw. Okay, let's see, maybe if I put something underneath, it's not, okay, let's do it like this. Okay, let's say that we have a set of states, right? And this, let's say, that is just made of 3 little dots, right? Then to be able to count how many elements we have, we would just use the counting measure, and so we just have essentially the cardinality of our set X. If you have, let's say, something that it's X cross Y, so let's say that we have a Y that it's made of 4 states, then we would have something like this, right? We would just have X cross Y for all the possible states. And so you would have that the total number of states, it's simply the product of the cardinality of the two things, right? So, you know, if this is red, green, and blue, and these are, I don't know, 1, 2, 3, 4, you would have all the possible combination of red 1, green 2, 3, 4, and so on. Okay, so this is how essentially it would work if the state space is discrete. And when you go to the continuum, you have the issue that if you have, if your X now it's a real number, right? You would have, let's say, a Lebesgue measure that tells you how big the set is, which basically tells you how many configuration you would have, for example, in position. And the issue is that if you now make a coordinate transformation, so if you make a Q that is equal a function of your old Q, then of course the sets become different, and so it wouldn't be true that the count of states is the same for all coordinate transformations. Some coordinates would be better because they would actually tell you how many configurations you have than others. And the way that this is solved in classical mechanics and also in quantum mechanics is that for every q you are going to have another coordinate p, and now you are going to have the product of two ranges, and so this is going to be essentially measured by your delta q and delta p. And the way that the coordinate works is that p's are covariant. So you have the q's that are contravariant, the p's that are covariant, and this essentially becomes invariant under your coordinate transformation. So your q stretch, your p shrink, and the volume remains the same, or your q shrink, the p stretch, and the coordinate is the same. So this is essentially how it works, that you have a count of states or count of configuration per degree of freedom that remains invariant under coordinate transformation. And this geometrically becomes the symplectic form. And so if you have a region U and you want to know how many states are there, you basically go and integrate the symplectic form. And if we want to write it in coordinate, you would write something like this: omega lowercase ab dx a dx b. That's basically what allows us to define the count of states in classical mechanics in a way that is coordinate invariant, and it's also what allows us to define an entropy that is coordinate invariant. So if we have a probability distribution, which of course it's going to be p, so it's the same number. So if you have a probability density, let's call it rho, which would basically be a dp d mu. This is your mu, this is the count of states, so mu of u oops, does it right again? No, this weird interface. Okay, it's not working anymore. There you go. Okay, so mu is basically the measure that tells you I have a set, how many configurations do I have, and you go and integrate the symplectic form, and now if you have a probability density, which is the probability per configuration, so it's the ratio between the probability and the count of configuration, so between the probability measure and the measure mu, then your entropy is going to be given by s of minus the integral of rho log rho in d mu. And so this is how you calculate the entropy, and everything is defined, and everything is coordinate invariant. Hamiltonian mechanics is just the preservation of this. So the real problem is defining these objects. And again, the interesting thing is that this omega defines the count of configuration per degree of freedom. And now, if you want to calculate the count of states, so the count of all the configuration of all the degree of freedom, you have a situation that is similar to what we have in the discrete system. You just multiply the configuration on one side with the configuration on the other side. So, for example, if this would be the configuration space for QP1, Q and P1, and this is Q2, P2, then if you have an area here and an area here, the total volume is just the product. And at the level of forms, you would basically just have omega, wedge, omega, integrated in your region U, and this is the count of states, which is just going to be the product of the count of configuration for each degree of freedom. Okay, so this is essentially how it works in classical mechanics. And the issue now is how do we generalize all of this for a field theory. So in a field theory, the degrees of freedom are at each point. So each point in space gives you a degree of freedom, and the value of the fields at that point will tell you the value of the degree of freedom. So now I have to figure out how to move this up and down. Let's see. How do you do it? Like this? Ah, there you go. Oh, and it's actually limited. Okay. I'll have to find a better tool than that. I hope everybody can read and follow this. Okay, so what we basically need to do, right, it's to say, okay, our Q's and P's, right, these were the value in each degree of freedom, and then we had an I that went from 1 to n. These were the count of degree of freedom, right? These need to become the value of the field and some value of a conjugate field that we don't know really how to define, and this is going to become the position in space, right? So that is what we need to do. So before, when we were in the continuous, right, we had a set X that was discrete, and we went to a continuous set that was Q and P, and we still had the degrees of freedom that were discrete, so we had 1 to n. So for mechanics, we did this step, and for field theory, we need to do this step and understand how we can carry these measures and the count of states, and therefore the entropy of this. And this is the part that I absolutely don't know how to do. And the reason is that a lot of the time when people just do this formal step from mechanics to field theory, they sort of carry over some symplectic structure in some way, but I don't think, or at least I don't know, how to make that the math that some people use fit this model. So I think that there are some pieces missing, and the main problem is understanding this coordinate invariant. That's basically the issue. A lot of the time, the symplectic form that comes out, or the integral of that symplectic form, it's not independent of the choice of units, and therefore it can't mimic the structure that we had. So if I need to be able to define a probability density on function spaces and all of that, and I haven't seen how people can do it. So in this configuration phase, you have uncountably many dimensions. You have uncountably many degrees of freedom. The dimension of space are still going to be the 3 dimensions of space, right? It's the dimension in phase space that becomes infinite, because now at each point in space you have a degree of freedom. And there is also an issue. So basically, right, the points become the field configurations, and so if I needed to specify the full description of a system, right, I would tell you what is f of x and what is g of x, in the same way that if I had to specify the state for a classical mechanics system, I would have to specify the q and the p, right? Actually, the qi and the pi. And so this would need to specify n numbers, right? N pairs of numbers, 1 for each degree of freedom. And now here you have an infinite amount of numbers that I have to give you, because I have to give you a pair of numbers for each point. And when we want to then create a probability density, right? This one, in classical mechanics, we would have a probability density for each possible set of values. And when we are in a field theory, I would be able to have a probability density that it's on each possible field configuration. And I have no idea how to do that. And when I talk to mathematicians about this, there are the two camps, one that says that it's impossible, and then the ones that do stochastic processes that basically say, oh yes, we do this all the time, right? And but they do it in a particular case where you have a signal that it's a function of time. So your probability is a probability on something that it's like, let's say, psi of t. Like you have a signal that goes in time, and then you say this, the signal has this probability of happening within the stochastic process and so on. So it's a little bit different from what we need because we need a probability on configuration on space, so that it's a function of space and not a function of time, and so I don't even know how much it carries over from one framework to the other. Okay, did that make any sense to anybody?
Yes, that made sense. Sorry, I was struggling to unmute.
Yeah.
Yeah.
Okay, so we can basically now discuss a little bit some of the things that how I think it could come, and how I think it should work. Unfortunately, this whiteboard doesn't seem be an infinite whiteboard, so I don't seem to be able to move it. I can only move a little bit around, but I would have to delete, which is kind of a pain. So, well, I still have some space here. I guess I'll use this space, and then I'll have to delete something. Okay, so basically, what are the things that we need to understand? So in mechanics, we had Q and P's, right? And then we have omega. So we have basically these three units. There are the units of Q. There are the units of omega. And then P is of unit omega over Q. Okay. So now what we have are the F's, the G's, and then we have to figure out what type of omega we need to have. But even for the F and the G, it's not clear to me whether these would be densities or would be fields themselves, right? So if F is a temperature, right, then that would not be a field that is a density, right? So it would just have units of temperature, and that's it. If we have something like the electric field, right, the way that the electric field is defined operationally is that you essentially measure the work per unit charge, and let's make a big Q. I don't know, when in physics of the 26 letter of the Roman alphabet, we basically use always the same 5, like P and Q's are always used for everything. But anyway, so let's do a big Q to say that that's the charge. And then this is going to be the integral of the electric field along the displacement on some path gamma. So technically, the work is the thing that we measure, the thing that we assign units to, and so the what's it called? The electric field is really units of work over charge over distance. Let's say L. And the point is that you never measure E directly. You always measure E as it is integrated on a line. If that is the case, if we change the units of space, right? You change the units of length. Not only we are changing, let's say, how we're representing the number of degrees of freedom, because now we go from 1 kilometers to 1 meter. That one, right? That range of one has now 1,000 fewer degrees of freedom to count, right? And so there is that. But then also the electric field, the value of electric field would change also because we have changed the units of distance. So it doesn't seem to me that the way that if we want to make all of these coordinate invariants and nice, if we treat a field like the temperature, it's not clear to me that you would treat it in the same way that you would treat the electromagnetic field. And one way that you can look at this is that if you, again, express the electromagnetic field in, what's it called, in component notation, you would write something like this: integral of gamma, E, let's say, over, let's use this, let's use an I, and then you would have a dxi. So you see here that the electric field has a unit dependence on the position because it's a vector, there are the components, and the components change in a different way, right? So yeah, so there is this extra problem, and the same thing for something like the magnetic field. The magnetic field would be, what we measure is actually the flux, and the flux is going to be the integral of the magnetic field on some surface sigma, and we have here a d sigma, and this, again, if we express it in component notation, would be something like bij dxi dxj. So all of this has to sort of work itself out in always expressions that are coordinate invariants, meaning that there is a resolution of all these units that sort of contract with each other, so you get invariance. And by the same token, it's not clear exactly to me what are the conjugate fields. So often the conjugate field of the electromagnetic fields, for example, it's essentially written as the potential. So the conjugate of, let's say, bij would be, and I need to write this correctly, bij would be, let's say, the vector potential ai, right? And so you can see in principle that these would, contract itself, but then you are missing this this j, right? And that's not an invariant. So the product of what is typically seen as the field and its conjugate, it's not an invariant. So it's not like here where we have the product of the Q and P is an invariant. So maybe we need some dxj, which means coordinates, which also means metric tensors, such that we do have an invariant of that, and then that would be the analog of the symplectic form. And again, I have no idea how to do any of these things. I just know that these are the pieces that needs to be made to work, right? And I have no idea how. So there is a comment from Ian. William Lever in the 60s started thinking about syntactic differential geometry. Specifically, he was trying to understand this. In this picture, you start with differential form in interrogator. So the problem of the differential forms is that, again, there is the whole issue of units that also I talked about in a couple of videos already, that somehow the differential form are not working well with units. So when again I look at some of these symplectic forms that people try to pretend that it works in field theories, because again there are some people that say they do, then there are some people that tell you that, oh no, it doesn't work, it's impossible. So I never understand who to listen to. But the problem is that the units don't work. But that's something that again. It's true even in classical mechanics, that we had to sort of reverse engineer some of these things and make them work better, because if you write, the form typically dq as a one form, the problem is that the components of the one form are covariant, right? So you should think as a one form as something that has the units down and not the unit up, because it's taking something and giving you an invariant. And here the form really has this unit up, like the Q is up, right? The Q should be down. And that's why I tend to write the omegas like this, because then it's clear that the symplectic form is a two form, and so the units are down. And to me, these are the standard differentials that you have in calculus, in differential calculus, the standard one, and these have units up. And now you have units up, the A are up, the A for the omegas are down, and then you get an invariant. So it's clear how the invariants are working, and it's clear the unit dependence. And a lot of the time when this gets translated in differential geometry with that notation, that this just doesn't work anymore. And so again, that's another extra complication that is given again by the problem that notation was developed by the mathematicians to solve some particular problem, because you want to look at essentially vectors and tangent vectors in a more algebraic way, so that you can do some things, which is all fine and dandy. But the problem is that it doesn't map to the physics, because the vectors are not operations in physics. They are, numbers that we can go out and measure, and we do other things with them. So that's again one of the issues that again I don't know how to solve. Connected to all of this, that we probably would also need to address is the whole thing about the Hodge duals. So in field theories, what we typically do a lot of the time is contract things with metric tensors, and you have your f alpha beta, right? And then you do your dual, star f alpha beta, I don't know how you wanna call it. And this is done essentially by contracting with a metric tensor, doing a bunch of things. But typically what you have is that in the f alpha beta, you have your homogeneous equations, and then I'm going to butcher them because I don't remember, but there should be something like this. And then on the dual one, let's call it hat just because, you have something like that. This is the J, and in fact the J is up, and so you need some metric tensor to make it go down, something like this. Let's see. And probably here there are people that remember these things better than me. It's been years that I haven't been seeing these things, but you're going to have something like this. You have the equations on the field are the one, you get the homogeneous one, and then you do on the Hodge dual, and you have the one with the charges and the what's it called, and the current, right? And again, this is something that comes up when we actually do field theories. And again, because when you do field theories, you are going to have a metric tensor, and I suspect that that metric tensor is telling us something about how you're counting degrees of freedom. I can only imagine that the size of a space is proportional to the number of degrees of freedom that you have, right? So if you imagine that you have a field configuration moving in space and you want your motion to be deterministic and reversible, you're going to have a configuration on a region of space. Well, and that region of space will have a number of degrees of freedom, then we will need to be able to say, okay, this region of space with a certain amount of degrees of freedom is going to be mapped to another region of space with, let's say, the same number of degrees of freedom. Therefore, we can now map to one the configuration of the degrees of freedom, and everything is nice and dandy. But if we spread that same configuration on a greater number of degrees of freedom, right, then something else will have to happen to the spread on those degrees of freedom, because we would like the entropies to be the same, the count of states to be the same. So if we are increasing the number of degrees of freedom, the spread of configuration in each degree of freedom would need to go down, so that the total number of degree of freedom would need to remain the same. So I think that what's happening, like the connection between let's say space, time, and entropy and all this, has to be of this nature, because it can't really be anything else. If we say that regions of space, at each point you have a degree of freedom, then we need a way to count those things, and then whenever we are mapping, and we are mapping the count of configuration, we need to be aware of that. So in this case, like in this slide, the field that is the metric tensor plays a completely different role than the other fields, because it's there to count the degrees of freedom that you have in each region of space, while the fields themselves are there to tell you what are the configurations that are there in each degree of freedom. And also that it's not clear exactly how it should work, and yes, this is yet another open problem that I don't quite know how to handle, but it should be clear that all these problems are related. You can't solve one without solving the other, and that's kind of what it makes it a little bit daunting, and that's why I'm not working on these things currently, because I'd rather fix things in quantum mechanics first and do that part and straighten out the math over there, and then once we have that, then I'll do classical field theory and so on. But if somebody wants to start tackling these problems and figuring out whether there is something already in the literature that would make sense, so that's kind of why I'm making this live stream.
So I know in the context of path integrals, it's apparently well known that you cannot put a sensible measure on the space of paths, or no one knows any.
Yeah.
Do you think this is like essentially the same problem, or are they related? Basically, finding a measure on. Well, now I'm thinking paths, which also kind of functions on some configuration space. While fields also functions, they just have, I guess, different output. Well, no, a path is a function into the configuration space. Anyway, do you think they are related, and are the results that are there somehow useful for us?
So they're totally related. The problem is that the path integral stuff is typically in quantum field theory. And in quantum field theory, the whole thing is made even more problematic because people want to use Hilbert spaces, as we have seen multiple times in this channel, in this project, in all the videos. there are problems already with infinities what's it called, in Hilbert spaces, because now the spaces of paths that you're considering are even ones that are discontinuous because they live in the Hilbert space, and you can do all sort of things there. And so I think there's an added problem there. So what would need to be done first, like that would be my strategy, is first to get all of this done well, like, squeaky clean, mathematicians approve in classical field theories. So that, first of all, you have to figure out what is the correct space of field configurations. Because again, it's not going to be the space of all the functions, and that would not make any sense whatsoever. I think even the space of continuous functions would still be far too big. I would even start by saying I have Schwartz functions for the fields, so that the fields are infinitely smooth and they decay faster than any polynomial when you go to infinity. And this also makes sense because whenever we do like Noether theorem type stuff in field theories, we always assume that at the boundary at infinity there's nothing going on, right? And that's basically what you want to do. That basically all your system is concentrated in an area, and then it goes in decays, and infinity there's nothing interesting. And so I would start by saying, okay, can we put measures that are nice and that work decently in the space of Schwartz functions? There are techniques that as I said before, they come from stochastic processes. There are things called cylinder measures, and they kind of work like this. Let's see. So the idea is, let's say that I have, I want to count, let's say that I have a space, let's say this is X, right? And on here we are going to put an F, right? And so your field configuration would be just kind of like a 2D function here, right? And now you're going to have a set of functions. You want to be able to say how many functions do I have. One of the things that you can do is, so first of all, you would like to say that you have, if you have a set of functions, let's say, if you count the function on this side, and then you count them on this side, right? The total number of function is the function that you counted on this side times the function that you have on the other side, right? So
are you looking at basically all marginals? Like
yes, like you chop your space in two, right? You look at how many spaces functions you have on one side, you look at how many functions you have on the other side, and then you basically can connect them however you want from one side to the other, right? And that would basically give you a product. There has to be some structure like that, in the same way that we said that there was even in the discrete, right? We have it actually already here, right? We have this, right? You want to be able to say, in these degrees of freedoms, I have this many possibilities, and these other degrees of freedom, I have these many other possibilities. I put them together, I have the product, right? And so you could start saying, okay, how do I count things if I have something that is generated in the following way? I have let's say, a compact region here, and then I also get a compact region interval here, right? So what you're basically doing is taking this thing, right? You're taking this and counting how many functions are there that stay within those bounds. And the obvious thing to do is to say, okay, I have a measure of x, right? This is going to be a measure of x. I have a measure on the f. I take the product. right? This, of course, would not be somehow invariant because now if I change f and a measure on f and I change a measure of x, I don't have what I want. And again, there should be the idea there should be a conjugate field g that somehow has inverse unit of x of f and inverse unit of x as well in such a way that now I have an invariant measure. Right?
Yeah.
And then you basically say, okay, if I can think that all my sets of the functions can be sort of divided up into pieces of x, pieces of f, pieces of g, and everything is the product of that, right? Then I can say, oh, I have a measure on the space of field configuration.
Yeah. Of course, you will have like compatibility conditions at the border and all that kind of stuff. If you restrict your function space too much and they become analytic, then you only need one neighborhood and you know everything, right?
Yeah.
So then the measure shouldn't increase if you increase the domain, let's say x. Yeah.
Well, you still don't know the derivatives, right? You only know the functions at the point.
I was thinking like if you just one open neighborhood, no matter how small, and then I allow any values in f and I measure how many functions are there, those would already be all the functions if I only consider analytic functions,
Okay.
for example. So then there will be the extreme case where everything outside of my neighborhood is like already fully determined by inside.
Yeah,
And you could have
but
something weaker than that if I don't know.
yeah, but then you would have that the degrees of freedom would not be independent because you're saying
Yeah.
if I know the function of this, and so the measure that you would put on x is not the correct one, right? Because
Yeah,
it is
those
not
are
true
not
that
independent.
yeah,
The field values are not independent. That's the point. Yeah.
yeah. So that's an interesting point. Like if the field values are truly independent, you can't limit yourself on the space of analytic functions. So yeah, so there are all these issues. I have no idea. Like it's a serious thinking that needs to be done.
Sorry if my add yeah I thought this would be like maybe less technical, but happily techniques are involved. And yeah, I was reading a bit about this, and whenever I try to find this well-defined measure, I see that there is one theory which sounds something like this, which is basically about triviality of translation invariant Borel measures. And it says that in infinite dimensional locally convex topological vector spaces admitting a countable neighborhood base, there is no non-zero sigma finite Borel measure that is translation invariant. And but what it often is concluded with is that if we want all these nice properties that we have in classical physics for particles, then either we end up with trivial measures which assign 0 or infinity to each point, or we need to start breaking these assumptions at some point. For example, if we break this translation invariance, then what we end up with is the approaches that use Gaussian as the background, because what we in field theories, entropy is often defined not absolutely but relatively, and but relative entropy behaves well, but we still need a reference, and this reference is usually the Gaussian reference, which is also connected to the fact that Gaussian is one of the few distributions that is stable. There is like Gaussian, Cauchy, and Levy distributions which are stable under convolutions with itself, and that allows some definition. And then there are these spaces called, what was it, Cartan-Merton spaces. I forgot which allow something, some nice behavior, but then the problem is that since we don't have this translation invariance, then as soon as we modify Hamiltonian just a bit more, that picture collapses, the measure collapses. So then the question is if this can be worked with. So this first approach basically is under the umbrella of abstract Wiener spaces. So I think also stochastic integrals are calculated in this way. The one approach with cylinder measures, where cylinder measure is actually cylinder pre-measure. It is not a measure. The measure
Right, yeah.
is obtained by taking a limit when it exists. But
Yeah.
the problem is that when it exists, it basically almost always collapses to the Gaussian background again. So it is, the question is like, if we want that. So that is the question. If we treat these fields as completely infinitely dimensional, or we say, okay, actually they're not infinite dimensional, but then we are limited to only a few of these modes or this cylinder-like projections, which basically removes, the bad modes and removes the inconsistency problems. Or if we are going, much even more, then we might think if we need this additivity, this Borel additivity, which means that then we lose any notion of measure. And in that sense, I see that people start using algebra of observables instead of counts of states. And then its approach is completely different. So, I think to start discussing, we should look at which assumptions are really crucial and which we can, let's say, give up.
Can you
So-
repeat again what the theorem was and what exactly was necessary?
What
Okay.
was that?
Yeah, let me find, because it was first developed in 40s, and then there was some work by Gross in 60s and 70s. But it says roughly that, okay, assuming it can be infinite dimensional separable Banach space, but it can be also more generally infinite dimensional local convex topological vector space, admitting a countable neighborhood at 0, and assuming that we have sigma finite Borel measure such that the measure is translation invariant, then the measures are either assigned 0 or infinity. So I might put some links later, because I took some papers, but now I have so many notes that I cannot scroll at the moment. But yeah, this means that there are different approaches.
Sorry, finish.
No, it's okay. Go for it. It's better that.
So if I understand correctly, you have a vector space with a topology on it. It's locally convex, which I always forget what it means, but I guess you have so you have a topology, you know what the Borel measure is, so you would know what your measurable sets are, and then you just put a typical measure on that. And then it says if you want that to be translation invariant, you can only assign it 0 or infinity. So the only assumptions are a vector space and a topology on it, and it's infinite dimensional, I think.
And it's translation invariant. I think
And
that is
translation
also,
invariant is key, yeah, which makes, I don't know, to me makes a lot of sense.
yeah, it is a separate condition. Like removing translation invariance allows us to define this, to use Gaussian background as good, background measure. It allows also, there is this, if I could find these names now, but there was an additional condition which assuming allowing only some finite energy perturbations, then we can define what is it? This radon derivative. which works nicely, but then we are limited to small perturbations of Gaussian fields. Otherwise, because it's again there is a theorem. I will put a name later, which means that if the basically if the Hamiltonian is perturbed, then that Gauss that either they have to be very compatible or they're like singularly different. So that there is almost like not even like nice translation between them. It's either almost of the same type or it's like completely different picture. But yeah, these names I just found them a few days ago. So it seems that it's using traditional approach is very how to say sensitive to perturbations. Yeah, so that was on this part, but I do not want to go to, too technical on this. I also wanted to add a couple of things maybe to this first part of the discussion regarding this electric and magnetic field. So first question, have you considered maybe using the full, how to say, using this relativistic approach of using Faraday tensor and this Lagrangian density and deriving momenta from there?
So yeah, we can go look at that, but you always have the issue of trying to understand what those things are. So like part of what we want to do, right? Since we do have an understanding what the Hamiltonian and the Lagrangian are in mechanics and what the action principle is in mechanics, so the idea would be really to understand what the Lagrangian densities and those things are, and again, it's I don't know how to do it. So it's sort of the same problem. Like if I knew how to do one, I would know how to do the other. Because
then,
like what we see in mechanics is that the Lagrangian is essentially the line integral. The action is the line integral of the vector potential of the flow states. That's basically what the thing is. And so if I knew what the Lagrangian was and how it works in field theory, right, it's going to be it's a Lagrangian density. So it's kind of like what I said before, per degree of freedom, because you're dividing by volumes of space, and the volumes of space are basically quantifying how many degrees of freedom you have, right? And so when you integrate that Lagrangian density over the whole space, you are finding essentially the line integral of the vector potential of the flow of configurations in fields, and so the thing should be that, obviously should be that, and then since the Einstein equations come out of that, and there is a nice relationship between the whatever thing that I don't remember how it's called of the tensor that comes out from the metric and the path integral. Then you'd be able to say, oh, okay, now I understand where the Einstein's equation come from, because they have to be about keeping everything, keeping the count of configuration the same. Therefore, as I was saying before, if space-time stretches, then the uncertainty on each field must go down, because you want the same number of configuration to be conserved. So there has to be something with those ideas, and I think that once we know the answer, it's going to be straightforward. But for the love of all that is holy, I can't get the details right, and it's all about details. Like I, in a vague way, what we have in classical mechanics is gonna fit the field theory, because it's the same thing. You have a Hamiltonian thing, so you're gonna have a definition of count of states. Your count of states is conserved, and therefore you have this Hamiltonian evolution. The other thing that it's difficult for field theory as they are specified right now is that they already have space-time together. And I think it would be easier to do first just things in space and evolution of fields in space, so that you basically have an equivalent of the classical non-relativistic mechanics, Because then when you go relativistic, there is all going to be the issue of, well, it's only volumes in space that quantify degrees of freedoms that are independent. Because at a later time, if I have a deterministic irreversible motion, obviously all the degrees of freedom in the past and in the future are going to be fully determined by the present. So they're not independent degrees of freedom, right? And so that's going to create even more of a complication of how do I count degrees of freedom when I have, surfaces and volumes that span space and time, right? And so I think that first we should solve that, and then once you start, it's going to become like this. Once you figure out one thing, all the other things will start to fall into place, because, as I said, it's always the same problem.
Mm-hmm. First, a couple of things about these electromagnetic fields. So if we take them in relativistic setting, then it takes some practice, but then although we know that these are components of the Faraday tensor, but but they can be extracted with certain projections, which basically requires contracting Faraday tensor with Levi-Civita tensor and with this for velocity of the observer, because these fields, depend on how you move through space, and there is this decomposition which can be used. Now, of course, in Newtonian setting, where let's say we only consider changes in space, it's trickier, but maybe it can be done. Another thing is that, of course, we are writing all these indices, sometimes Latin, sometimes Greek indices, but we should remember that, just because it has an index, it does not mean that it is a covariant quantity. That has to be checked independently. So, for example, Levi-Civita symbol, as this, a permutation symbol itself, it is not a tensor, even though we use it in relativity very often. But playing with this volume measure, we can see that it is something like tensor density of some weight, and it can be recovered. It's basically, you can start with, let's say, flat space where there is no measure, then you switch the coordinates, and then you see that there is the square root of determinant. And the trick is basically you take, what is it? A square root of this, to both sides, so it looks, equally weighted on both sides, and then voila, you have, Levi-Civita tensor, or like the tensor, the density, appropriate one. So this could be done with other objects as well. But yeah, I agree that first we need to, to understand how, how to make our descriptions covariant, because this is sometimes is completely neglected. For example, in quantum mechanics, the basic quantum mechanics, questions about covariance treatment, even for, just in space, is absent. You cannot find it.
Right. So in quantum mechanics and field theories, I've seen things that absolutely make no sense. Mm-hmm. So one of the things that, because there was a colleague of mine that was trying, he has a different way to do field theories, and was asking me for some suggestion and so on. And we were looking at a way to do, because he wanted to do Fourier transforms in curved coordinates and stuff like that. And the thing that we saw was that they were using the wave function. They were doing the Fourier of the wave function as if it were a scalar function. Huh. And the wave function is actually the square root of a density, because if you square it, you get a probability density. And yes. So they were literally using the wrong way to do a Fourier transform, and they, articles and articles all citing this thing, and it cannot be correct.
Also, with this Fourier transform, I think people are so attached to it because, in flat space and Cartesian coordinates, it's very simple. But also, this Fourier transform sometimes is assigned, a larger meaning that it actually has, which is that it is, an eigenfunction of some operator. If you switch to different coordinates, the eigenfunctions change, and then this trivial, a naive Fourier transform might not even have a meaning. So instead, instead we end up with these spherical harmonics, which are not so nice to work with. But that's what what we have in the end. But yeah, I agree that this is often missing. Yes. So just last comment, and I'll give floor to others. So yeah, I found the names. So there was a statement going back to this infinite dimensional spaces. So let's say we lose this translation invariance, then we can define this background Gaussian measure, and then there is then the question is what kind of perturbations of this field we can allow. So we have something more than just Gaussian. Usually, arbitrary perturbations will destroy the meaning of measure, but there is such thing called as Cameron-Martin space, which is basically how to say, it's a smaller space, it's a subspace of these perturbations, and then it admits a shift of measure which is absolutely continuous. So it has a nicer meaning, but then otherwise measures of original system and perturbed system will be mutually singular. And that is basically what it ends up. But yeah, if we limit ourselves to this Cameron-Martin space, then the behavior is, let's say, manageable. So I'll just post it in the chat for people to be able to see it. And otherwise, yeah, I think that's all. I think other details I will try to paste in the Discord.
Yeah, like so the way that I think the theorem that you stated works is basically the space becomes too big to put a uniform measure. Like it's a little bit like you're trying to put a uniform probability measure on R, right? And either it goes all to zero or all to infinity. That's basically it. So I think there's going to be something like that. Because the locally convex topological vector spaces that are second countable, if I remember correctly, they're not locally compact. And so if you have something that it's not locally compact, probably you're going to have some issue of the same type. Again, it's a little bit out of my league, but my intuition would be that that's basically what the problem might be. But that doesn't mean that we can't put probability measures, because probability measures are not at all translational invariant. So maybe, maybe the point is going to be, yeah, you're not going to find a measure like that, and it's okay, because what you care about doing is something else that I don't know what it is right now. So a lot of the time when I couldn't find the right math to do it, then I saw, oh, actually, I actually want to do another thing. So even here, really what we want to create is this analog of the symplectic form, right? And so we want to basically just do things for infinitesimal pieces, right? And the infinitesimal pieces that we have are all things at this point that looks like R. Because the space is going to be R3, and the values of the fields are still going to be some type of Rn, because it's like you have n fields at a point and you want to describe them. So the only thing that you need to do is essentially some type of form on the variation of these things, and then being able to integrate it. And maybe that's a much lesser requirement than the everything. And because once we know how to compute these things piecemeal and do our things, maybe that's going to be enough. Because at the end of the day, what we want to set up is the machinery to do essentially a symplectic field theory. That's the only thing that we need strictly to do.
Yes, so indeed, although we cannot recover all these properties, I think, for example, this conservation of Liouville measure or Liouville volume, maybe it cannot be derived, but there are other notions which exist in some similar or version like in we are used to. So,
Yeah.
but that needs to be picked up. Yes.
Yeah. So we basically, yes, don't have the full measure on the whole space, but we have these, piecewise things that, yes, they're going to sum to infinity. And, if you do the thing of the whole thing is going to be bad. But, or you could also argue that, if the sort of these spaces go down to infinity, and you want things to go down to infinity, maybe this translational invariance is not there anyway, because you will want your ranges to go down at infinity anyway, so maybe it's not a problem. I don't know, right? But the thing is that, right, since we are physicists and we come from the physics works. So since the physics works, there has to be a nice and clean mathematical way that underpins that physics that is working. We just need to find it.
Yes, and also we can discuss these complicated mathematical theories, but then we need to attach to physical intuition, like what is happening, what do we need? Does it make sense that we can measure the fields with infinite precision at every single point?
Right. So I really think that there's going to be a solution, and once the solution comes, it's going to be physically obvious and mathematically clean. Because every time that I set myself to do these things, to my surprise, that's what happened. And then at this point, I always expected, because, yeah. The math is just there to characterize your physical specification, and if the math is not clean, it's just because you haven't specified the physics right. Once you specify the physics right, the thing is gonna come.
Mm-hmm.
So let's see. There were a couple of comments from Ian. Geometry from order, causal set, it's a discrete model of space-time as finite set in spatial. So the problem that I have with things that starts finite and then they want to recover things is that we kind of so one of the things that both topology and measure theory told me is that the points are not important. The sets are what's important. And so you don't really care what you have what type of if you have accountable points or whatever. Like we want to have a characterization of these sets, and then we have found that those sets have a very, very nice characterization in terms of empirically testable statements. So when we have a region of the phase space U, it's because we can ask the question, is the state of the system within that space, the region of phase space? So is the position of momentum in this bound such that they're there? And all the topologies and all the sigma algebras are generated from that. So I'd much rather have those as starting point instead of some underlying sets or some other structure that then it becomes the thing that we want, because I want to start with the thing that I want, which is the connection to experimental verifiability, so which is the sets. And since even there in topology and in measure theories, for the second countable spaces, which are the things that we are interested on, the things that can be generated by a countable collection of empirically verifiable statements, because that's it. We're never going to test more than those. These things can even be all described without the points. Like the points can be recovered. They're really like throwaway things that you use, and so I never, like, if there's something that starts with the points and then does something, I always feel suspicious. I don't think that they're capturing the correct physical requirements, because the physical requirements are going to be in terms of experimentally verifiable statements. Well, we've done an hour and 10 minutes. Let's see if there are more questions. We didn't touch the whole Lagrange and stuff, but I think it's going to be a repeat of the same problems anyway. It's not going to add that much. Okay, so we close it here. No more questions, so we still have to figure out what to discuss next week. If there is nothing on the table, I could talk a little bit about topologies and sigma algebras and how we physicists are like behind 100 years in terms of thinking, because we haven't digested these things. And also I myself, I'm only now in the past 4 weeks I can finally understand infinite dimensional spaces and how should I think about it in physics. So I can chat a little bit about that if there are no other topics. But if somebody wants to suggest a topic, that would also be fine. Okay, so bye everybody. Thank you for participating. Thanks Ian for the questions, and I'll see you next week.
See you. Bye.